All right, we're here. We're at the end of chapter 1, lesson 1.6, where we're actually talking about solving absolute value inequalities. Our objectives for this lesson are to determine how we can use compound inequalities to solve absolute value inequalities. Then how do I translate absolute value inequalities that are combined with a less than or a less than equal to symbol? And how do I translate absolute value inequalities with greater than and greater than or equal to symbols? So those are kind of our three goals. So remember when we were solving absolute value equations, we were looking for a range. We could go off to the left, we could go off to the right, and we had to translate the single absolute value equation into two equations without an absolute value. This is going to happen again. So what concepts have we been discussing that also apply to a range of values? Well, hopefully you're thinking, well, that compound and the compound or. How can we use these compound inequalities to help us solve absolute value inequalities? Well, what we're going to do is we're going to translate absolute value inequality into a compound inequality, because we know how to solve those. We just have to determine whether we write it as a compound and or a compound or. So let's consider how we translate an absolute value with less than or less than equal to symbol. What's going to happen, we're going to see, is it's going to translate into a compound and. So let's start with this simple example. Absolute value of x is less than 3. Let's graph it and see if we can see which graph it represents. If this is 0, and I count 3 spaces to the right, I'm at 3. If I count 3 spaces to the left, I'm at -3. This says I have an open circle and an open circle, and I want values that are less than 3 units. So that would include -2, -1, 1, and 2. If I go to beyond 3, then I haven't met the criteria. If I go beyond -3, I haven't met the criteria. So what does this equation look like, or graph look like? Well, it looks like a compound and. And how do I write this algebraically? Well, I'm going to take a -3. I'm going to take my variable. I'm going to take +3. And I'm going to put less than symbols in between them, just like that. So let's use that to help us solve absolute value inequalities with a less than equal to symbol. So notice that I've already completed this step right here. I took the opposite of 3, which is -3. Then I used the expression inside the absolute value, and then I used the positive of this number, right? Now I have a compound and now I'm going to isolate my variable x by subtracting 1 from all 3 sections. And I get -4 is less than or equal to x is less than or equal to 2. In set notation, I get bracket all x's such that -4 is less than or equal to x is less than or equal to 2. To write that in interval notation, I get bracket because that's what this symbol implies. And then comma 2. And then this symbol implies that I need to use a bracket again. So here's 0 on my number line, and here's 2. -1, -2. Can you guys hear the fireworks behind me? -4. Closed in circle. Closed in circle. And a line in between. That's a compound and. Let's try one more. All right, we're going to rewrite and translate into a compound and. So we get -17 is less than or equal to 5x plus 2 is less than or equal to +17. I took the opposite. I took the expression, and then I took the positive. I'm going to subtract 2 from all three sections. I get -19 is less than or equal to 5x is less than or equal to 15. Now I'm going to divide every section by 5 to get that x, to get it off that x. And I get -19 fifths is less than or equal to x is less than or equal to +3. And I'm going to write it in set notation here. Interval notation is bracket -19 fifths comma 3 bracket. When you're using absolute value inequalities, your symbols at the ends are always going to be identical. Here's 0, 1, 2, 3, -1, -2, -3, -4. Not quite -4. -20 over 5 would be -4. So I'm going to call it here close dot. And 3, close dot. And then a line in between. All right, now let's start looking at a compound or absolute value with a greater than symbol. Greater than, or, notice what we have here. Okay, so what we're going to do is I'm going to graph this. Here's 0. And then let's see, I'm going to go up by 2s. 2, 4, 6, 8. -2, -4, -6, -8. So we want more than 5 units away from 0. So let's do the positive first. So here's 5. So I'm going to use an open because this indicates that I need to use an open. And then I want more than that. So I don't want to go towards 0. I want to go away from 0. And then I can count 5 units to the left, right? 2, 4, 5. So here, and that would be open. But I want more than 5 units, so I don't want to go to the right. I want to go to the left here, right? So this is x's that are less than -5 or x's that are greater than +5. All right, so we're going to write it like this before we start solving. So let's translate this into a compound or. We try and write small enough to do this. We have 2x minus 6 is going to be less than -12, or 2x minus 6 is greater than 12. Okay, let's kind of separate this. I'm going to add 6 to both sides, and I get 2x is less than -6, x is less than -3. 2x is greater than 18. I added here. I added 6 to both sides. I'm going to divide by 2. X is greater than 9. So I'm going to go up by 3's. Here's 0, 3, 6, 9. There's -3, -6, -9. I need values of x that are less than -3, open for less than without the equal component, going off to the left, and then greater than 9, again open, and going off to the right. In set notation, I have all x's such that x is less than -3 or x is greater than 9. Notice that I write the smaller range first and then the positive or larger range second. Excuse me. In interval notation, -infinity to -3, union 9 to positive infinity. In this case, because this is exclusive, all of my ends are parentheses. All right, now we're going to translate a graph into an absolute value equality. You need to know 3 things. You need to know if the graph is an and or an or. Is the graph an and or an or? Okay. So you know how to tell that. We learned that. If it's between the 2 endpoints, then it's an and. We're going to find the centering number using the midpoint formula. That's the second thing we're going to find. And then 3, we're going to determine the distance that each endpoint is from the center. And watch your scale. My examples, every slash is 1, but in the book, I don't know that they are. I don't think that they are. All right? Then we're going to plug everything into this expression right here. Okay? So this is an and. Let's change to a pen. And. Okay, my centering number, that means I have to find the midpoint, okay, between the endpoints. So -3 plus 2 divided by 2 is equal to -1/2. So here's my center. And then I have to determine, that's C, and then I have to determine the distance that the center is from the endpoint. So I'm just going to count 1, 2.5, 2.5 units. And now I'm going to start plugging in. All right, I have absolute value x minus a -1/2, right? This is an and, so an and has to be less than. The endpoints are included, so it has to be less than or equal to 2.5. That's the absolute value expression. One more simplification, x plus 1/2 minus a negative goes positive is less than or equal to 2.5. Our last slide. Determine if the graph is a compound and or. These are going off in 2 separate directions, so this has to be an or. Our centering number, we're going to use the midpoint, -1 plus 3 over 2. That's going to give me a 2 over 2, which is 1. The distance, here's my center right here. The distance is 1, 2. So D is equal to 2, and then I just plug in to the formula. This is an or. An or has to be greater than or greater than equal to. Look at your endpoints. They're included, so it has to be greater than or equal to. X minus 1 is greater than or equal to 2. All right, here's the problem set. Remember, Quizlet is due on Friday. Thanks for listening, and I will talk to you tomorrow.